to give me like a 10-minute warning. I have not practiced this talk. I might go over time or under time. We'll see. But hi, I'm Michael Arntzenius. I'm a postdoc at UC Berkeley, and I'm here to talk about finite functional programming via graded effects or co-effects. It'll turn out not to make a difference, and relevance types. So what we're going to be doing in this talk is trying to use fancy types to deconstruct logic programming into functional programming, because that's kind of a hobby of mine. The motivation here is that I like functional programming and I like the relational model. So I like functional programming. I like higher. Is that legible to people in the back row? No.
It's good.
I don't know whether there's any way to make it bigger. Well, that cuts off the top, whatever. Yeah, I like higher order abstraction from functional programming. I like his ability to do modular programming. Functional programming is great, but the relational model is also great, as I was discovered from working at a database company for 2 years. It lets me separate what I'm doing with my data from how I'm going to be representing it or how it's going to be executed. And we know a lot of good, efficient strategies for executing relational style queries efficiently. So I want Datalog, but with higher order abstraction and modules, and this is work in that direction.
Maybe this is a bit pedantic, but I noticed you say functional programming, but you say relational model.
Yeah.
You don't like programming. Relational programming.
I mean, I like relational programming because I like the relational model. I don't like the inability to do higher order abstraction. Yeah, and also this work came out of my time at a company called Relational AI, which was building a Datalog with higher order features that looked a lot like, if you squint, the language I'm about to present here, but it was all implemented as basically macros that took your higher order stuff and turned it into first order stuff that was crunched on by a Datalog engine. And it worked remarkably well, and I didn't understand why. Why doesn't this pile of macros come apart at the seams? This is my attempt to figure out why this thing might be reasonable to do in the language of type theory, because that's my native language. All right, here's a logic program. We're trying to model a social network. We've got a follows relation that says, you know, this user follows that user. Ada follows Bob, Ada follows Charlie, Bob follows Ada, a lot of other facts in that vein. Okay, so when are two people mutuals? Well, X is a mutual of Y when X follows Y, and Y follows X. Pretty simple. What is a relation? It's a function into booleans. It tells you whether a thing is in the set or not in the set. I know about functions and I know about booleans and I can do those in functional programming languages, so what happens if I just do that? Follows is a function that takes a person and yields a boolean. Follows xy is true if x is Ada and y is Bob, or x is Ada and y is Charlie, or x is Bob and y is Ada. You just write down a bunch of ors and ands. That denotes the same set that's denoted by follows on the left. How about mutuals? I can do that too. Mutuals xy is follows xy and follows yx. So these programs should denote the same thing. They do denote the same thing, but they don't feel like the same program. And that's because I can't do the same things with them. In logic programming, or databases, or relational programming, whatever you want to call it, I can do things like enumerate all of the inputs for which a relation is true. Or, for instance, I can find the mutuals of a given user. I can say, hey, who are Bob's mutuals? Functions are input-output black boxes in functional languages. I can't do this. I can pick two users and ask whether they're mutuals, and then it will do this very slow backtracking search through all of the possible matches here. Imagine there's a million things here, or a billion, right? It will give the right answer, but it will be slow, and it does not let me enumerate things. It just lets me test. For an example of where this analogy completely falls apart because of this inability to enumerate things, let's say, like, on the left, we've got a logic programming which says, like, this director has worked with this actor if there's some film that the director directed that the actor acted in. Easy peasy. This is a relational join. Okay. In functional world, sure, I can assume I have these functions, and then I can define directed actor how exactly? Where does this film variable come from? Well, what's the semantics of the thing on the left? It's true if there exists a film such that the body is true, such that the director directed the film and the actor acted in it. So if I imagine a magical exists function that takes a function from films to booleans and tells me whether there's any film that makes it true, then I can write this easy. Right? Does there exist a film that the director directed and the actor acted in? But how do I implement exists? I need to like enumerate all possible inputs to it, and this is just a bad idea. Maybe there's only finitely many films, but there are a lot of them. I don't actually want to test every single film. This is not how the logic program works. It's not how a relational join works. So what I want is that this function from film to bool has to be able to tell me what are the inputs on which it is true. I want functions that aren't just input-output black boxes. I want functions that can tell me what inputs they yield true on, or what I'm going to call their support, the inputs they produce something interesting on. I'll define this precisely later. In this talk, I'm specifically going to focus, because I am Datalog pilled, on finitely supported functions. So how do I enumerate the results? I have a freaking table of them. I have a table of all of the input-output pairs that are interesting. Okay. Everybody good so far?
Maybe a general question. So you say you model relations as functions to booleans in the functional programming. Another option would be like more like non-deterministic functions, like using the list monad.
That's another way of doing it. It's not the way I'm doing it here. Maybe we can talk about the pros and cons at the end. I like thinking about them as just functions because it lets you be very direct about what you're saying. It looks nice. It's maybe an aesthetic opinion. But yeah, there's definitely a monad hiding here, kind of. Okay. Any other questions, especially anybody confused? If you're confused at some point, do not hesitate to jump in. I may defer other questions to the end. Okay. What do I mean when I say the support of a function? Well, we've got sets. I hope people know what sets are. If you don't want to talk about sets, you can talk about types. I don't care. A pointed set or a pointed type is a set with a default value, which I'm going to call nil. So with booleans, by fiat, the default value is false. So then a supported function, the support of a function into a pointed type, a pointed set, is just by definition the inputs on which the output is not nil. Right? So these are the interesting outputs, right? Nil is the boring value, and everything else is interesting. And then a function is finitely supported if its support is finite. And this is how I'm going to write the type or set of finitely supported maps from a set to a pointed set. Also, this type is pointed. Its point is the function that is everywhere nil. That is the boring function. This will be useful later. Or later, I think, is the next slide. Okay, why am I bothering with pointed sets instead of just using booleans? This was about logic programming, right? Like, all we need is booleans for logic programming, right? Yeah, kinda, but there's several good things that come out of going beyond the Boolean black and white world. First off, it's going to let us give interesting types to or and they will be different types. Or and have different types, which I just find really cool. We'll get to it. This also allows us to curry things, right? So I can speak of a finitely supported function into the space of finitely supported functions. This is a natural way of talking about finitely supported functions of multiple arguments, and we're functional programmers. We know the value of currying. I'm mostly not going to talk about these things, but it also gives us a natural story for aggregations, which are finitely supported functions into, I don't know, like the reals or the naturals or some type that isn't Booleans. And it lets us do weighted logic programming. And there's been a bunch of interesting work here using semirings. So I like these reasons, but in this talk, we'll mostly see these reasons. So the goal here is a language that looks functional and is functional. It has procedural functions, including higher order ones, but it also has a type of finite functions, right, which are guaranteed to be finitely supported by the type system, which are going to be represented as tables, and which are going to be computed like database queries. And I'm mostly going to focus on this in this talk. I have ideas about this. Come talk to me afterwards, but the talk's mostly about one. here are some examples of what programs in this language should look like. Right? Like I can define when two people are co-stars, and this should be, finitely supported in 2 arguments, right? When are they co-stars? If there is a film that they both starred in. I can find the number of films that an actor has starred in. This is also finitely supported, but it's into the naturals. This is an aggregation. It says, take the sum over every film when the actor has acted in it, produce 1. Otherwise, implicitly 0, because 0 is nil for natural numbers. And as a stretch goal, which I will not be able to get to into this talk because I don't know how to do it, I want recursion. I want to be able to define these relations, these finitely supported maps, recursively. So like, let's say, talk about people who are connected through the graph of co-starring in films together, which will be, just about anybody. As it turns out, all actors have, are connected to all other actors. So when are 2 people connected, right? When is there a path from them? If they co-starred together, or there's some intermediate actor Z, such that X co-starred with the Z, and there's a path from Z to Y. Yep.
Well, that's, oh.
Ask that question at the end. Okay, how are we going to do this? How are we going to come up with a type system for a language like this? Our first insight is that this thing, this type of finitely supported maps, is a graded co/monad, by which I mean it's a graded monad and also a graded comonad. So what is a graded monad? And what is a graded comonad? Well, they're kind of like monads, right? A monad we might think of as like, forget about this subscript A here, right? And pretend all these isomorphisms are arrows going to the right. I have a return function that takes a P and produces a TP, right? It embeds the thing in the monad T. And then a join function, or oh, I called this return, that's wrong. Join, that takes a TTP, a computation that yields a computation and produces just a computation. Okay, a graded monad is when actually there's a subscript on it, and that subscript acts in an interesting way. There's some identity thing. When I return, I get T with the identity annotation, and when I join, I multiply the annotations together. So here, our annotations are themselves types. They're sets. The identity is going to be the unit type, and the way to combine them is going to be take the cross product. Right. And so what is going on here, in fact? Well, not only do we have arrows going this way, which is the monad direction, these things are all isomorphisms. We have arrows going in both directions, which is why it's also a comonad. So what's really going on here is like, look, if I have a pointer type P, that is isomorphic to having a finitely supported map from the unit type into P. Because like, there's only one input. What's the value of that input? That's the P we're talking about. And the other direction is just currying and uncurrying. If I have a finitely supported map represented as a curried thing, that's the same as having a finitely supported map whose arguments are pairs. But the reason this is nice is because graded monads and comonads have been extensively studied, and we have typing rules for them. And I will sort of be using those typing rules, but they will look funny. But there's another thing that we need to be a graded comonad. We need this thing to be a functor. We need it to have a map method. What is map for this type? The naive answer is, okay, give me a function from P to Q, give me a finitely supported map into P, I will apply this function to every one of its values and get a finitely supported map into Q. Except I won't, because this is not guaranteed to be finitely supported. Why not? Well, let's say the function that I'm mapping over the values just returns true all the time. True is not nil, it is an interesting value. No matter what my initial finitely supported function was, I get the function that's true everywhere. That's not finitely supported. So what I really need is that the function I'm mapping over it should preserve nil. It should do nothing to boring values. It should not touch the things that are not in the table, right? This guarantees that I only need to apply the function to things actually in the table. Everything else was mapped to nil, and it preserves nil. So let's talk about functions that preserve nil. Yes?
Just making sure I understand. So the monad is only defined over pointed sets, and map is only defined for functions that preserve nil. So what you're saying is it's a graded comonad in the category of pointed sets, not in the category of sets.
Correct.
Okay.
Yeah. So we need to talk about the category of pointed sets, and point preserving maps or nil preserving maps, which are just functions on pointed sets that preserve nil. F of nil is nil. Okay, this is not only a set but a pointed set, which is good. Nil is again the function that's nil everywhere, the boring function. And now we can talk about the type of map. Map takes a nil preserving function from P to Q. It takes a finitely supported map into P, and it produces a finitely supported map into Q. And it also preserves points in all of its arguments. So, just like you said, it's a functor on the category of point preserving maps. And this is useful because this is how we manipulate values that are in our finitely supported maps. Or, well, this is the one of the ways we do it.
The first thing you wrote was just like nonsensical.
Yeah, that's just incorrect. That's why it has a big red X next to it. This is the type you might naively write down if you, yeah. I mean, I think I did write this down at some point, and then I was like, wait a minute. Okay, so going back over all the stuff that we've developed so far. What time is it? Okay. If A and B are going to represent sets, P and Q stand for pointed sets, we have three different kinds of function. We've got regular old functions, which I'm mostly not going to talk about. We've got point nil preserving functions. Both of these you should think of as being procedures, closures, normal. And then we've got finitely supported maps from a set into a pointed set. These you should think of as if they're tables. What are our typing rules for pointed sets and point preserving maps? Is lambda x.x a point preserving map? Yes. If I feed it nil, I get nil out. It preserves nil. How about lambda x.true? Anybody? I see some shaking heads. Yes, there's a big red X next to it. It does not preserve points because if I feed it nil, like false, for example, I get true, which is not nil. It doesn't preserve nil. So that's interesting. This tells us our type system is funky. Normally, you can write constant functions. How about lambda x.foo(x) and bar x, where let's assume foo and bar are point preserving, or nil preserving. Well, if I feed it nil, foo(x) will be nil because foo preserves nil, and bar x will be nil, and nil is false, and false is false, and false is nil. So yes, I get out nil. So this is an interesting type system. I have to use my variables. I'm not allowed to not use them. I'm not allowed to use constant functions. But it's not linear types. I don't have to use them exactly once. I can use them multiple times. That's fine. It's not affine types. That allows you to drop things. That would allow me to write this. It's relevant types, which is not very commonly seen. This is the type system of at least once. You must use your variables at least once.
If you have a nil function, the boring function, is that also a constant function?
So that's the one kind of constant function that is okay. So I can show you the typing rule for nil. The typing rule for nil is special. Lambda x.nil does type check. Yeah. Nil basically lets you throw, you can have any number of inputs and produce nil and you're fine. Yeah.
So it seems, at least from the three examples, I'm convinced that relevance is like a potential over approximation for nil preservingness, but it seems like it could be a very large over approximation of nil preservingness.
What kind of over approximation do you mean? Sound or unsound or sound?
It is sound, but certainly not complete.
Yeah. True fact.
How big is the gap?
Let's talk about it at the end. It's significant. I have some ideas for how to tighten it up, but I think at the end of the world, you're gonna need either a bit of theorem proving or a bit of trust me in your type system.
Can bar be a normal function here? Because
yes.
Okay.
So
you have combinations of that.
yes, the typing rules for tensor are interesting, and we are going to get them, assuming we have time. But yeah, the typing rule for tensor product is funky. All right. As foreshadowed by that previous answer, there are two kinds of products here, as you might expect from a linear logic-like thing. There's two kinds of interesting products in category of pointed sets. The simpler one is with or direct product, which the values are just pairs. And the nil is just the pair of nils. Easy peasy. or has the type bool with bool, point preserving map to bool, because it produces nil if both of its inputs are nil. And that's kind of the idea of this kind of product. It is useful for representing functions of multiple arguments, which produce nil if all of their arguments are nil. But that's not the only interesting kind of point preserving function on multiple arguments. There's also what if I preserve nil separately in all of my arguments. If any of my arguments is nil, I produce nil. Well, that's what and is. And produces false if any of its arguments are false. And for that, it would be safe to give and this type. It would be sound. But because the typing rules for tensor product allow us to do more, we want to give it this more precise type, where tensor product is this. Tensor product is pairs quotiented by if either of the components of the pair is nil, it's nil. So nil comma y, same thing as nil. X comma nil, same thing as nil. So the only interesting values here are the pairs where both things are interesting. So we have two products and we need different typing rules for them. Yeah.
Isn't and an isomorphism though?
Yes. Okay, what are the typing rules for these things? These are not the typing rules for these things because we're still missing a context, but we're going to start with just two contexts. We've got our context of sets, which we're allowed to do with whatever we like. We've got our context of pointed sets, and we must preserve point in all of these, all of the things in this context. So our typing judgment is going to look like this. Gamma delta entails T of type P, and it means we got a function from gamma into a point preserving map from delta. The rule for with is extremely straightforward. It's literally just, this is nil if both of these are nil. So we give the same point preserving context to both of them. But the rule for tensor product is more interesting. This is going to be nil if either T or U is nil. So what I can do is I can split up my context. I can add some of it to T and some of it to U. Because remember, this context is nil. When is this context nil? If any of the things in it are nil. It's implicitly a big tensor. And that means this is nil if at least one of the things in it is nil. So if I split it up, these things are both point preserving. So at least one of them will be nil. This is a tensor product, so that means this will be nil. So this allows us to split variables up, but we don't have to. This is why I've written a union here. You could totally pass the same argument to both. It's fine. That's why this is relevance typing, not linear typing. Yeah?
In the gloss there, the delta is the tensor product of everything in delta.
Yes.
Okay, cool.
Yes. That is important, and I didn't write it.
So if you have an empty delta context, there are no nils in it. There it's not.
The tensor product of nothing is booleans. So there's two things you could substitute into that. You could give it false, in which case your result has to be nil, or you could give it true, which is the interesting case. Yeah. The identity of tensor product is booleans, which is a bit weird. The identity of regular old product is the singleton type, which only has nil in it. I recommend not thinking too hard about the empty context if you want to get through the rest of this talk. All right. What else have we got? Okay. I've written down this typing rule. Oh God, right. Now, I wanted to write down lambdas, which stood for finitely supported maps, so I need 3 contexts. I have 3 types of functions, so I need 3 contexts. So we're complicating our typing rules again. Now, we've got 3 contexts, and this means a map out of gamma, a point preserving map out of the tensor product of the deltas, a finitely supported map out of the product of the omegas into P. Here is our typing rule for with. It is, again, very simple. Yeah?
You can take it at face value if it's helpful, but can you give any intuition of why it's this particular order of contexts when I'm elaborating into an arrow? Like, why is it that order of arrows?
Because that's the order that made my example programs work out. In fact, I think that you're going to need an arbitrary sequence of alternations between deltas and omegas, but I didn't want to make these typing rules even more complicated. Yeah. Yeah, but most programs seem to be typable with just this. So this typing rule is still like you just pass the same context to all of them. It is worth thinking about why it has support, right? What is the support of this thing, right? These things are supposed to be finitely supported. Okay, so if we have some value for gamma and some value for delta, and we know the support of t at that gamma and delta, and we know the support of u at that gamma and delta, what is the support of the pairing of t and u? It's the union, because this thing is non-nil if either of its inputs is non-nil. But the union of finite sets is finite, so we are fine. Okay, I'm going to be a lot less precise about tensor product because there are many more rules. Which of these functions ought to be well typed? Which of them actually has finite support, assuming f and g have finite support? F of x and g of y, one thing, f of x and g of x, and f of x and x is above 17. Anybody want to guess? Are there any of these that are ill-typed?
Last one?
What?
The last one?
Good guess, but no, none of these are ill-typed. They are all finitely supported. Why? What is the support of this thing? It is the cross product of the support of f with the support of g. Because, well, I mean, it's non-nil if f of x and g of y are both non-nil, and it's producing an x and a y. Support of this is the intersection of the support of f and g, right? In order for this to be non-nil, both of these have to be non-nil. The support of this is the support of f filtered by being bigger than 17. And I can take a finite set and filter it by anything I goddamn well please, it's still finite. So all of these are finitely supported. And they all need different typing rules. Okay, what's the typing rule for this thing? Or rather, they need an escalating sequence of increasingly interesting typing rules. The typing rule for this thing is sort of just, okay, I'm passing part of my context, my finitely supported context, to t and part of it to u. Why is this okay? Well, you can think of it as being because I have a finitely supported, a point preserving map of this shape, right? Or you can just think of it, I'm not going to go into that. You can just think of it as like, look, the support is the cross product, right? So plainly, I can pass part of my context over here, part of my context over there. Each of these is finitely supported. The support of this is the cross product. That's still finite. How about this one? This is justified for a slightly different semantic reason. It's justified because the support is the intersection. So, you know, I take the union. That's basically the same as for some of them I'm commaing, and for some of them it's the same thing. So the interesting addition of the previous one is that I can let the indices of my graded comonad be the same, and I still get out this thing. And then the final one says, hey, look, if my first thing finitely supports this set omega, I can actually then use those arguments however the hell I want to. This omega 1 moves, it jumps contexts from the finite support context in my first argument all the way over to the unrestricted context in my second, which allows me to apply an arbitrary function, not finitely supported, not point preserving, nothing, just any old function you want in the second argument, because you're just filtering down the support of the first argument, and that's fine. So this is a combination of filtering down and cross product, and also intersection. So this is the most general typing rule.
This looks like the notion of prior safety in databases.
Maybe? I'm not familiar with that, despite saying database, database, database.
It's just the idea that the relational algebra indefinitely produces infinite results.
Yes. Yeah, exactly. That's what I'm trying to ensure.
So it's not commutative?
What?
So it's not commutative?
Haha. I have chosen not to make it commutative. In principle, it should be commutative, but I didn't want to make the typing rules even more complicated. Yeah, so you have to think about the order you put things in to make sure things ground from left to right.
So isn't the first rule and the second rule the same?
No.
Why?
Because in this rule, the variables have to be distinct that I've passed between them,
Yeah,
right? Whereas in here, I can have the same variable appear in T and in U.
sure. Let me rephrase it. Isn't the first rule a sub-rule of the second rule?
Yes, yes, this is more general.
Okay, yeah. But the third rule is not more general.
I think it is actually. Find me a counterexample.
Like, what is the third rule need to be a union?
I don't think you need it to be a union because I think you can always just pick all of the variables that occur in U that also occur in V and put them in omega 1 and they go here. Yeah.
Yeah, okay, okay.
All right, so what the hell is the typing system we've come up with here? Yes?
Still the terms to witness the.
I conjecture that you can always find an order to put them in by using let expressions so that it grounds properly, but I don't have a proof.
So, I mean, that often happens in stuff. You can still like laboriously sort of rewire things.
Yeah.
Particularly like session typing systems where we have hats are interpreted in a strange way.
Interesting.
Send an A and then behave like B. It looks like it's not used to the thing.
Yeah.
But it still derive.
Yes. Yeah, although here it's non-commutativity on the level of sort of the terms, right? Like the order in which I put my term in might make a type check or not, but you can always, I think, find a program that makes a type check that has the same semantics. Fingers crossed. Okay, what is the type system that we just come up with? So far, it looks kind of like it's just relevance typing again, but with that weird, funky last rule. But it's not. Let's look at our examples to figure out why. Here are our three example functions. Here's whether they preserve nil or not, assuming foo and bar do. Now, if we assume foo and bar are finitely supported, which of these are well typed? There's exactly one that's different. There's exactly one that is different in this column versus this column. Anybody want to guess? Yeah?
Identity?
Correct. The identity function is not finitely supported, right? Take like the function lambda x.x from the naturals to the naturals, where 0 on the naturals is I don't care, like 0, nil on the naturals 0. That has infinite support. All of the naturals other than 0 are in my support. It's not finitely supported. It's also not even well-kinded. Finitely supported maps are supposed to be from a set to a pointed set, but like this is from a type to the same type. They can't. So I can't even express that. But even if I could, it would be wrong. But this is well typed. So what's going on here again is I've made this context, but it doesn't correspond to a category. There is no identity map. It corresponds to a graded comonad. So what do my typing rules look like? What are my introduction and elimination rules for finitely supported maps? The intro rule is very boring. To make a lambda x.t, I put x into my finitely supported context. That is what it is there for. It's the elim rule that's funny. The elim rule says, if I have a finitely supported map, I can apply it to a variable, and then I can throw that variable away and check that this is finitely supported. So the way you eliminate finitely supported variables is you apply a finitely supported function to them. You ground them. You make sure that there's only finitely many values they can take on such that my expression is not nil. So the way you get finitely supported maps is from other finitely supported maps, which means you need some primitives that generate finitely supported maps, or else the type is empty. But this is still not quite right because I put a comma there. What if I want to take some function and apply it to the same argument twice? This is actually perfectly fine, right? In terms of support. So I need to make that thing a union. And now I can take a finitely supported map of two arguments and apply it to the same variable twice to diagonalize it. So, okay. So how do I actually make finitely supported maps if the type system doesn't, let me write down, doesn't have a variable rule? Well, here's one way. Equality. Give me a value. There is a finitely supported map out of that type into Booleans that is true exactly for that particular value. More generally, if you give me a value, a key, and a value, then there's a finitely supported map that is nil everywhere except at that key for which it produces that value. It might be nil there too if you happen to give it nil, which is why this is a point preserving map. Then there are a bunch of functions for combining things. We already saw or and. And so, you can use those to combine maps that you already have, right? That's what foo(x) and bar(x) is. It's an intersection of sets. You also have a function like when, which says, look, if I've got a boolean and a value, well, I'll give you nil if the boolean is false, and I'll give you the value if it's true. So this we saw way back in some of the example program I wrote about summing up all of the films, right? Finding how many films an actor has appeared in, right? We also have a whole family of aggregations, right? So we saw exists. If I have a finitely supported map from some type into booleans, I can tell you whether the support is non-empty, right? Like, look at the table. Is the table empty? Then false. If the table has a thing in it, then true. But also, since the table is finite, I can sum up all the entries in a table whose values are natural numbers. Or I can take the minimum of a table whose entries are natural numbers or infinity, and infinity is the default value, because infinity is the identity of minimum. Yeah?
Can exists work with a different pointed set other than bool?
That's what these are.
Oh, yeah, okay.
Yeah, that's the idea, right? Things that have a type of this shape, right? A finite support into P, point preserving map into P, are aggregations. This is the story for aggregations. And in fact, one can conceive of a type class, right, which is things which are additive in this way. I need a function add that takes P with P to P, which has the property that adding nil does nothing, and it's commutative and it's associative. And then I can lift that to a summation function that sums up all the entries in some finitely supported map. Yeah?
I may want to do some other kind of product. Does that fit into this pattern somehow?
Product is point preserving with identity 1. So it would fit into this if you had the naturals where the point is 1.
Yeah, as you said, it's the type actually contains the point.
Yes, the type contains the point, which is awkward because there's a lot of possible points in the naturals. Right? How do I define types? I don't have, I don't have a great story for doing that. So this is the bit where there's a gap between like soundness and completeness. It's like, how do you get all this information into the type system? So at some point, some sort of trust me feature where I just define some trusted primitives and everything else works out compositionally. And like, there's even an example here. I say, if I have an add satisfying these laws, then I can get a summation function, but I can't define that inside this language. It needs to be a language primitive to lift an add, which is associative, commutative, and preserves nil into a summation function. 10 minutes, cool. We're nearly done. So what this talk should have been called was lambda, the ultimate relation, but I didn't think of that. The one thing you take away, if you take away nothing else, is relations are functions plus support. Relational programming is functional programming where we care about the support of functions, where they're not input-output black boxes. They can tell me the inputs for which they have an interesting output. I've talked about finite support because I am a Datalog head. I suspect that the same story would work if you cared about innumerable support, and then you'd have something that's kind of like Prolog. I think this approach is nice because it naturally handles weighted logic programming, which I think is cool, and aggregations, which I think are very practically important, although only some aggregations. Aggregation is hard. The type system is ugly as hell, but I love it. It is the funkiest type system I've ever thought of, and there's no dependency in it. Don't have to have dependent types to have an interesting type system. It's got graded comonads, it's got an adjunction. There's an adjunction between set and pointed set that I didn't talk about. It's got relevant types, and it's got a lot of fiddly little details. And there is more that I did not talk about. And with that, I'm going to open up the floor to questions.
What do you mean by enumerable? Aren't all finite sets enumerable?
Oh, I mean, if you wanted to loosen it from being finite to being enumerable.
Oh, I see.
Yeah, yeah, because in Prolog, your relations aren't always finitely supported. Yeah, although I'm not sure even enumerable is correct for Prolog because it can represent like, you can just define a predicate that's true everywhere in Prolog, which is not necessarily enumerable. I mean, like it is if your type itself is enumerable, but like It's some sort of more symbolic representation of the support.
It was a very nice image.
I don't want to answer that question.
I asked about recursion.
Oh, God. Yes. Why is recursion hard? So, okay, no, I'm not going to go all the way back to where I mentioned it because, well, I think recursion is hard because it means various different things. And so depending on what you want, you need to figure out how all those things interact. So in Datalog, when we define relations recursively, what that means is sort of you have a rule for defining the relation based on itself. You start out by feeding it the empty relation. And then you get a slightly larger relation. You feed that in, you get a slightly larger relation. You do that until you get a fixed point. So it's sort of bottom-up fixed points by iteration. I know how to do that. In functional programming, what fixed points mean is basically laziness. I define a function with respect to itself, and that works out because it can't call itself until you call it. And then you add non-termination in order to make it all work. That's no problem. But how do I combine those? I don't really know. Because now I've got non-termination mixed up in my fixed point loop. I think so. The problem would be ensuring termination of your fixed points, your bottom-up fixed points, your recursively defined relations. Because as soon as you have the ability to add one to a number, you can define an infinite relation, right? I can define like foo holds of 0, and if foo holds of x, then it holds of x plus 1. That's infinite, and therefore kind of non-terminating. And so how do you forbid that? So ensuring totality and having recursion is hard. And for the functional programming side, we know how to do like inductive things, and we can ensure termination there. I don't know what a nice equivalent story. I have some ideas about that. But I don't have a nice equivalent story for relational recursion. And I kind of don't want to. I'd rather have general recursion. I want a story that works for general recursion.
Isn't it a lot easier, maybe it's not, theoretically, if we think about enumerable things rather than finite things, because then you don't have the +1 forbidding problem?
It makes some things easier, but it makes some things harder. Like if the support is enumerable, and then I take the sum, that could be infinite.
Yeah.
So you could just say, well, if it's infinite, you're hosed. And that would be one approach.
Why not have yet another sort and effect system? We need an effect system. That's just fun.
You could try that. You could try to know whether your things are going to be enumerably supported or finitely supported and put that into the type system somehow.
Yes.
Ugh. Yeah.
So on the slide where you had like the 3 different typing rules for tensor increasing generality, I noticed that like on the first 2 you had like, oh, here's some nice category theory words that are explaining what's happening. For the last one, there was no. So I'm curious if there's like a principled way that you like arrived at this rule. I think there is some like more interesting like math going to like justify why this like works.
Very roughly, I don't know. I arrived at it by looking at this function and saying, yeah, that ought to be grounded. That ought to be finitely supported. Like this is a totally standard thing to do, filter down a set. And I was like, okay, this seems like the typing rule I need. Can I give it a support? Can I figure out what its support is? And is it going to be finite? Yes, I can. I did not have enough space on the slide to fit in the showing that its support is finite, but it's not too hard. Is there some categorical account of this? I would love to hear of it if there is one.
So you introduced the graded monad/comonad. One important thing is what are the assumptions you place on the algebraic structure forms the grades. So that question, does it relate to the centerings that you mentioned in one of the possible applications?
No, I don't think so. In this case, the grades are types, or in practice, they're going to be contexts because that's how I'm using them in my typing system. And so I am being a little fast and loose here because like normally in a graded comonad, you need the grades to form a monoid, but A cross B cross C is not the same type as A cross B cross C parenthesized the other way, but they're isomorphic, and these are all isomorphisms, so it should work out, I hope. Wave hands here. but I don't think it's connected to semirings. Semirings actually go here. They're the pointed types, right? A semiring is a pointed type with an additive structure and a multiplicative structure on it that both work out together. Yeah, is that clear enough? Okay.
Just making the point that context for monoid, so I think you're fine. You just, tensor out in the last stage.
Yeah.
Yeah,
Yeah, I guess.
Yeah.
Okay.
Have you considered like allowing more interesting interleavings of, sorry, I know you considered this because you mentioned it, but are you working towards allowing more interesting interleavings of the 3 different types of arrows that you have?
I have
the 3 zoned context.
Yeah, I have like thought about it, but I haven't really worked on it because again, these typing rules are already at the limit of my ability to think pretty much. I'm trying to find the slide. Whatever. This slide has this on it, which is good enough. The thing that I think you need is, yeah, so gamma is always at the outermost, I think. I'm not even entirely sure about that. But you can definitely have like delta, omega, and then another delta, right? Because you can have a finitely supported map from this into like a point preserving map over here, right? And those do not commute, right? A point preserving map into a finitely supported map is not the same as a finitely supported map into a point preserving map. You can't move the arguments around. So you need your context to reflect that. And that's basically as far as I've got in thinking about it.
So I agree that like semantically gamma does have to be all the way at the left because like things in gamma don't necessarily have a nil. It doesn't make sense to put them anywhere else. But I think syntactically it's going to be a little bit annoying. So I think your type system is a really nice typing for greater than on nats because it's the greater than function on natural numbers.
Mm-hmm.
So it goes like nat, normal arrow, nat, finitely supported arrow, O.
Correct.
So that means I think you could do with your fun typing for and, you can do great things like 5 greater than x and x and x greater than 3 is completely finitely supported and so on.
Yeah.
But I don't think you can write that for less than, which is a bit unsatisfying.
Yeah. True fact. I don't know how to solve that either.
Like, have you considered like just solving that with, I don't know, like syntax hacks where all of the gamma-like things are semantically pulled to the left, even though you could just write them wherever you want?
Yeah. I have not considered doing that because I would need a system that actually like runs examples to care about figuring out how to do syntax sugar. And this is all pretty much theory at this point.
Okay, so last question. Yes. Have you considered an effect system in an SMT solver?
No. What would the SMT solver be for?
Well, because presumably once you have your effect system, you can then tag your functions with predicates like preserves nil or finitely supported or so on and so forth, and then just put in all the facts you're allowed to use and see if it's set.
Right.
Implement type system. My favorite categorical.
I kind of like having a type system rather than throwing an SMT solver if I can get away with it because it's much more predictable what things are going to type check. The place where I would consider throwing an SMT solver at it is for like, sometimes there's point preserving functions that I don't know how to get the type system to know are point preserving. So I'd sort of like to implement those as like little primitives, right? Like here's my custom user-defined type, here's my custom user-defined functions on it. And then instead of just telling a type system to trust me, throw an SMT solver at that little chunk of my program, and then do the rest of the program compositionally. So if I were going to use an SMT solver, that's how I do it.
But yeah, you can have your type checker just have nice SMT instances, just like a fast cat.
Let's talk about this offline.
Okay, so let's speak again.